I'm an industrial automation engineer. My day-to-day involves looking after massive machines, making sure they run safely and efficiently every hour of the week. These machines stay on track using something called a feedback loop. It's a simple three-step process. The machine measures what it's doing right now, compares that to its target, and then changes its behavior to close the gap. This loop is the essential starting point for automation. Without this constant self-checking, a machine is effectively operating in the dark, unable to see or react to the world around it. Historically, the simplest way to control a machine was a basic on-off switch. Imagine a heater in a chemical plant trying to keep a liquid at exactly 100 degrees. When the temperature is at 99 degrees, the heater blasts at full power. But even after it reaches the 100-degree target and shuts off, the heating coils stay hot. That residual heat causes the temperature to spike up to 105. Now the system is too hot, so it stays off until the liquid cools all the way down to 95. Then the power kicks back on at 100%, and the cycle repeats. This constant overshooting and undershooting is incredibly inefficient. In engineering, we call this wild, uncontrolled swinging oscillation. Oscillation is a nightmare for a factory. It can ruin sensitive chemical products and wastes a lot of energy. If you apply this jerky on-off logic to a heavy robotic arm, the physical stress will eventually shake the entire machine to pieces. Simple switching doesn't work for high-precision work. To move safely, a machine needs to be able to steer smoothly, gradually easing into its target. This is where the PID controller comes in. It's a mathematical smart driver that looks at the present, the past, and the future to steer the machine. The first part is the proportional term, or P. You can think of this as the gas pedal. It decides how hard to push based on the current gap between the machine and its target. If the machine is far away, the controller pushes hard. But as the machine gets closer, the controller begins to let off the gas, pushing more and more gently as the gap shrinks. However, because the push gets lighter as the machine gets closer, it often stalls out just a few millimeters short of the goal. The gas pedal is being pressed so lightly that the machine can't overcome basic friction or its own weight to finish the trip. Because real-world machines always have some resistance to movement, reacting only to the present gap isn't enough to reach the target with perfect accuracy. To fix that, we use the I, or integral term. This is the machine's memory, and it looks backward at past errors. The integral term notices if the machine has been sitting just below the target for too long. It starts adding up those tiny errors from the past. As that total sum grows, it provides a slow, steady nudge that gives the machine the extra power it needs to overcome friction and land exactly on the mark. By learning from its own recent history, the integral term ensures the machine finishes the job instead of stopping just short. Finally, we have the D, or derivative term. If the first two terms are the gas pedal, the derivative is the brakes. It looks ahead to predict where the machine will be in the future. It measures how fast the machine is moving toward the target. If it sees the machine is approaching too quickly, it realizes an overshoot is about to happen. The math pushes back against that speed, slowing the machine down as it arrives. This predictive braking ensures the machine lands perfectly without any shakiness. You can see this logic in action with heavy robotic welding arms. These tools are massive, yet they need to glide into position with zero jitter. This predictive math is what allows them to move such heavy loads with such high precision. When you combine these three, present, past, and future, you convert a jerky, dangerous machine into a smooth and reliable tool. In the real world, PID controllers have to be tuned to fit each specific machine. An engineer has to adjust the settings for each part of the math to find the right balance. Imagine a robotic arm that's swinging back and forth past its target like a pendulum. We can see that the system is being too aggressive. To fix this instability, we turn down the proportional gain. Think of gain as a volume knob for the math. It controls how loudly the system reacts. Turning it down means the system won't stomp on the gas pedal so hard. Now, what if the machine is moving smoothly, but consistently stopping just short of where it needs to be? Here, the engineer would turn up the volume, or gain, on the integral term. This forces the machine to care more about those past errors, giving it the push it needs to reach the target. Sometimes a machine will start to jitter nervously. This is usually caused by electrical noise, essentially signal static that makes the sensor readings look fuzzy and inconsistent. If that happens, the derivative term might be overreacting to that static. We can solve this by lowering the derivative setting or adding a filter to smooth out that fuzzy signal. Tuning is a vital skill. It's the process of looking at a physical problem and knowing exactly which mathematical dial to adjust to fix it. Smooth, reliable automation depends on a system that is constantly reevaluating its path every few milliseconds. A moment of wonder. This simple-sounding formula is actually the hidden logic behind everything from hovering drones to the robots that perform delicate surgeries. Proportional, integral, and derivative control is the invisible smart driver that keeps our modern world moving precisely on track.